Welcome to our last video in virtual physics. Thank you guys for a good year. This video is going to be going over the review, and then as a little bit of a thank you, I'm going to give you guys a little bit of a gift at the end of the video. Also, a thank you for actually watching this video, which I know some of you guys don't do, but that's fine. So, number one says, explain some reasons why we changed from a geocentric model of our solar system to a heliocentric model. That's because we noticed retrograde motion, and we noticed that the planets moved in peculiar ways. So, number two, in your own words, explain retrograde motion. Retrograde motion is the appearance of a planet slowing down and then reversing direction and going in the opposite direction. In other words, retrograde motion is when we as a planet on the outside are, on the inside are being passed by a planet on the outside of us, or we are passing a planet on the outside of us, and that planet on the outside looks like it's slowing down, but in reality it's not actually slowing down, it's that we are passing them on the inside. Number three, use Kepler's first law to explain why the following image is incorrect. This image down here, the sun wouldn't be in the middle, it would be in one of the two foci, which is Kepler's first law. Number four, using Kepler's second law, explain why the shaded areas have the same size, because they're moving in different speeds. Remember, that's the huge part of Kepler's law, is that they're different speeds, so as they go closer to the sun, they're going faster, they're covering the same area, though because it's a small, because they're close to it, so there's not as much length here, but there's more width because they go faster, right? More width here, but less length. So when they're over here on the opposite side at aphelion, they're moving slower. There's more length but less width. Number five, use Kepler's third law to calculate an orbital period. So for that one, I used p squared equals a cubed. Rearranged it so p was by itself. P equals the square root of a3, a to the third power. So 12 cubed. Square root that, and I got 41.57 years. The next one, this one was kind of confusing for some of you guys, but you just needed to count these boxes really. So you can see here that the foci are at -5 and 5. I just decided to use this one as my foci. It really doesn't matter. And then the very center of the ellipse is at 0. I'll skip the eccentricity for right now. So if this is my foci, there's only one box from -5 to 6 to -6. So there's only one unit that's that distance of perihelion, where they're the closest. Now, if this is our foci, the sun, all the way to the other side would be our aphelion, and that would be 5 and then 6. So there's 11 boxes between the foci and then the other side. So the aphelion is 11 units. To get the eccentricity, all I had to do is use my knowledge that it's the distance between the foci divided by our major axis. So our major axis in this case is 12, right? We just kind of talked about that. So 12, and then you divide it by 10, you divide 10 by 12, because 10 is our focal distance, 5 going to the center, and then another 5 going to the other side. So there's 10 units between the two foci. So 10 divided by 12, you get 0.83 is your eccentricity. For the next one, you had to match the vocab. A lot of these are from our more astronomy-based stuff, and then some of them are related to gravity. So ellipse is just a flattened circle. That's B. The semi-major axis is E, the longest point or longest distance from the center of the ellipse to the edge. The perihelion is J, the shortest distance from the sun to the planet. Gravitational constant is A, 6.7 times 10 to the -11th. The solar day is C, the period of time from one sunrise to the next. Lunar eclipse is K. This is when the Earth blocks the sunlight going to the moon. Aphelion is I. This is the longest distance from the sun to the planet. Phases of the moon, D, the changing amount of moon that is visible at night. H is eccentricity, the amount the ellipse is squished, and it is equal to the distance between the foci divided by the length of the major axis, which is what we just went through when we calculated it. Heliocentric, this is F, a model of the solar system with the sun in the center. Orbit is L, the path the planet takes around the sun. Solar eclipse is G, when the moon blocks the sunlight from the earth. If I went through those too quickly, please make sure that you guys go back through, rewatch the video, or pause it after I've said them. Please let me know if you guys have any questions on these definitions. For number 8, these are the problems that are going to be very similar to what you guys are going to see on the quiz. So please make sure you guys do spend some time thinking through these and being able to do this math in your head. Number 8, if the Earth suddenly doubled its mass, what would happen to the gravitational force between it and the moon? That would also double. We're not changing the distance, and we're not changing the mass of the moon. So we are just changing the mass of the Earth, and in this case we double it, so we double the force of gravity. 9, if the moon suddenly doubled in mass, what would happen to the gravitational force between it and the Earth? It would also double. It's important for this one that you guys to realize that it doesn't matter which mass you double, as long as you double one of them, that's going to have a doubling effect. Number 10, if the Earth suddenly doubled its distance, so in other words, it's increasing the distance from, let's say, 2 to 4, right? What would happen to the gravitational force between it and the moon? It would decrease, right? I think we all know it decreases or goes down, but it doesn't go down to a half of what it originally was. It goes down to a fourth of what it originally was. So, for example, if the force between the Earth and the moon was 40 newtons, it would go down to 10 newtons, right? Not 20. So number 11, if the Earth suddenly moved twice as close to the sun, so in this case we're bringing it way closer, then what would happen to the gravitational force between the Earth and the sun? It would increase to 4 times what it originally was. So if it was 40 again, if it was, let's say 40 because it's between the Earth and the sun, then it would go up to 160, right? It wouldn't double, it would go up to 4 times as much. What is Newton's law of gravitational, or of universal gravitation, and what does each variable represent? So force of gravity is equal to the gravitational constant times mass 1 times mass 2 divided by our distance squared. So that's what's shown here. Again, a lot of you guys are getting confused by the big G. This is just our gravitational constant, which if you remember was 6.67 times 10 to the negative 11th, or 6.7. Some people just put it that way. Little g, when we're talking about little g, that has nothing to do with this formula. Little g is the acceleration due to gravity strictly on the planet Earth, right? If you want to figure out the force of gravity between any two objects, doesn't matter what mass they have, doesn't matter what planet they're on, etc. Between just two objects and you know the distance, you would use this formula. Alright, if I asked you to find the force of gravity on me and I gave you my mass and I told you I'm on Earth, then yes, you could use little g. Right, but in this case, you should always use this formula, and you're always going to use big G in this formula. You never use little g in this formula. Number 13. 2 students are solving for the gravitational force between the sun and the Earth. Student A says that we must use double the gravitational constant because the Earth and the sun are very large. Student B says that we cannot change the gravitational constant. Who is correct? Why? The reason that we call it a constant is because it stays constant. It does not change. So it doesn't matter where you are, it doesn't matter what objects you're looking at, you are going to keep the gravitational constant the same. So I would agree with student B. 14, draw a graph that shows how gravitational force relates to mass in the space below. So I drew a straight line here because if you double the mass, you double the force of gravity. So these are a direct linear relationship. As you increase one, you increase the other. As you decrease one, you would decrease the other. 15, this is the opposite. This is an inverse relationship, and also notice that it's not a straight line because if we double the distance, the force gravity goes down, but not by a half. It goes down by a fourth. So that's why I drew a curved line here. Also, it's important that you know that it's inverse relationship. In other words, as you increase the distance, the force gravity goes down, right? Which is opposite of the force gravity and mass. As one goes up, the other goes up. This one is as one goes up, the other goes down, right? So number 16, I apologize for how weirdly formatted this is. My printer apparently was not a big fan of how I formatted this worksheet. So anyway, this one is going to require you guys to do some calculations. So if the mass is of one object is 330 kilograms, the mass of the second object is 250, and the radius between them, or the distance between them, is 750 meters, then what is the force? So in this case, I just plugged all my numbers into the formula up here, big G, or the unit gravitational constant, multiplied by the mass 1, mass 2, divided by our distance squared. I got 9.78 times 10 to the negative 12th. So what happens to the force gravity on the second object? Because that was the force from the first object. What about the force from the second object? Those are actually equal, right? It doesn't matter which object we're talking about, right? You pull on the Earth just as much as the Earth pulls on you. So if we change the mass to 660, so in other words, we double one of the masses here, what would happen to the value? You would notice that it just doubles. It goes from 9.78 times 10 to the negative 12 to 1.96 times 10 to the negative 11th. If we change the mass to 125, so in this case we are cutting it by a half here, you notice that this goes down by a half. We go down from 9.78 times 10 to the negative 12 to 4.89 times 10 to the negative 12. If we change the value for r to 375 meters, so we're cutting the distance down by a half, this should go down 9.75, it goes 78 to 2.45, so it goes down to a fourth of what it originally is. And notice that this is confirmation that we were doing these ones correctly. For the last one, also notice how those numbers are so small because our masses are very small, and we have we don't have any planet-sized objects here, so that makes sense. For this one, we have very large objects now, so we are going to end up with a mass that is more of a realistic big number. So in this case, I plugged my numbers in. Force of gravity equals the gravitational constant times mass 1, so 6.67 times 10 to the negative 11th times 4.3 times 10 to the 13th times 1.4 times 10 to the 6th, which is our second mass. All of that is divided by our radius of 3,500, and I need to square that, and I should get 327.78 newtons, or 328 newtons. Okay. So notice that you need incredibly big objects to get numbers that are actually somewhat big, right? Here, if you have small objects, right, you're going to have very small forces of gravity. And then finally, 18, this one is just really asking you how well you know your scientific notation. I'm not going to be quizzing you on this, though. So anyway, you would turn the first number 2.6 times 10 to the negative 4th. You move the decimal 4 times to the right. 1.2 times 10 to the 9th. You move the decimal to the left 9 times. Finally, number 19, you need to move these numbers back to normal notation, so it's 0.0003075, so I had to move my decimal 4 times, and then 12,430,000 is your number for this one, so 12, 43, 4 zeros. So you had to move your number 7 times, or your decimal 7 times for that one. And lastly, as a thank you for not only a good semester, but also just for watching this video, which again I know some of you guys aren't doing, so this is my thank you for watching my videos and my content. Here's two answers to some quiz questions. For object A, gravitationally attracts object B with a force of 10 newtons, then object B will gravitationally attract object A with an equal force of 10 newtons in the opposite direction. That is true. Right, I know I mentioned that in the review. It's true. Object A and object B are pulling each other equally, so true. Make sure you put true for this number. The force of gravity between two objects is 20, and one mass is cut in half and the other doubles. Meanwhile, the distance doesn't change. What is the new force? That is going to be 20, because really the mass of the entire system has stayed the same. You cut it in half, but then doubled the other one, so that it stays at 20. So there are two answers on the quiz. If you've watched this video, I'm sure you'll do well anyway, but I wanted to give you guys a little bit of a thank you for watching all my videos. Anyway, so have a great summer, guys. Please make sure you guys do fill out the last question and take it seriously. I appreciate your guys' responses there. Alright, have a good day, guys.